Yes, sir.
Okay, thank you for the feedback. All right, let me share my screen. Okay. All right, good afternoon, everyone. Okay, before we start, I have got an announcement to actually make on the 14th of April, which is, I think, on Thursday. We are going to have a quiz. We will be having a quiz, and this quiz lasts the whole day long. But what you need to do is actually to spend 10 minutes for you to answer the quiz. And this quiz is actually counted. There are some marks given to the quiz. Of course, this is not the only quiz that we will be getting. This quiz cover learning unit 1 until learning unit number 3, 1 to 3. So do some revision, especially look at the tutorial questions to help you with your quiz preparation. Right. And as we have actually mentioned in our chat group, that the group assignment has already been announced, been released. So please form your group, and then the group leader should do the coordination to gather your group discussion to make sure that everyone playing their role. I know you do not get a choice to choose your own group member. I think there's an advantage lah. I just put you to face the real world a little bit earlier. When you actually enter the workforce, you have no choice. You cannot choose your colleague. You cannot choose who are your colleague, but you just have to deal with them. So your group member also, I do not allow you to choose. I will randomly choose for you. So you just have to deal with them lah. I know some of you may don't like it, you see, because you may see that some of the members are actually free rider. Okay, these are the problems. So this is actually a problem that all the group member will have to deal with lah, to make sure that everyone contribute towards your assignment. Okay. So these are the things. All right, so let's let me see. Let me get started. Let me put on the chat. Yeah. All right, let's get started with this one. And this learning unit, we're talking about data and signal. So basically, we will look at transferring of data across the networks. So normally, what are we transferring? We are transferring things like images, file, all sort of files that we are transmitting. But how do we transmit them? You see, how actually those data be transmitted over the network? And I mean, more specific term, how those data be transmitted over transmission media. So a lot of times, if you talk about digital data, we are transmitting basically 0 and 1, you see, because all the digital data are actually represented by 0 and 1. So what is being transmitted are actually 0 and 1s only. It's basically a stream of 0 and 1s. So how does this thing happen? And as we all know that, the digital representation is only something that the microprocessor, which is actually a computer system, can understand only. But in the actual communication network, we still have to rely on some of these, physical element to actually do the transmission. So how does it work? And a lot of times, we are using electromagnetic signal. basically electrical signal, electrical current, okay, to actually transmit the data across a transmission medium, okay, regardless of whether they are guided media. Guided media means copper cables, fiber optics. Oh, sorry, my fiber optics are actually using optics, using lights to actually do the transmission. But most of the copper cable type of transmission media, we are actually using electromagnetic signal. It's basically running on a frequency so that you can use your current to actually deliver your data. Your data is supposed to be 1 and 0, but your electrical current, your electrical current are actually not 1 and 0. So how do you put your data on this signal so that this signal can carry your data all the way to the destination? So this is exactly how we want to look at today, which is actually the data representation of how those are the fundamental characteristics of electromagnetic signal. Okay, so if you look at this diagram here, and you can see that your computer is basically generating digital data 1 and 0. Okay, you are seeing those 1 and 0 here. Let me draw a bit. Okay, your computer generating digital data 1 and 0, which is actually the natural state of your microprocessor. Your microprocessor can only generate 1 and 0. So in order for you to actually transmit it over a link, I would say a link, which is actually a transmission media. So you will have to, go through a modulator. Why? Because the link is on the physical copper cable link. What can only be carried by this link is only the analog signal. It can only carry analog signal. And then only analog signal can travel physically. I would say the signal physically travel through this transmission link. And you may ask about how about digital signal? Yes, correct. Digital signal is a different thing. We will have digital data to be put on to digital signal. And we have to make use of a device called modulator. Modulator is actually to perform a modulation, signal modulation, to modulate 0 and 1 into an analog signal. It is something like just like you get on a bus. So your digital data need to get on the bus. What is the bus? The bus is actually the analog signal. So your 1 and 0 need to get on the bus. And how do you get on the bus? You have to go to the bus station. And this bus station for this computer network is actually a modulator. So your digital data, through the modulation process, it will get on to the analog signal and then be carried by the analog signal all the way until you reach your destination, which is actually you go through a reverse process, which is actually going through a demodulator to recover your digital data. This is something like you reach another bus station. Is it destination bus station, and then where your data get off the bus, where you get off the bus. So this is actually what happened. And then if you look at the diagram below here, you can see the analog signal can be shaped in such a way that to actually carry 1 and 0. So if you look at the first one, this bit of the analog signal is actually high frequency as compared to another one over here. This is low frequency. So you have one. Sorry. Where is mine? You have 1 and 0. 0 is low frequency. 1 is high frequency. So you can use high and low frequency. This is just one of the example high and low frequency to actually carry your digital data by the analog signal. So we're going to look at some of the more detailed process after this. So some of the things that we need to understand here in this learning unit is actually we need to understand what's the difference between analog and digital. What is the difference between analog data and digital data? The difference between analog signal and digital signal. Okay? Analog data is actually your voice. I just give one example. Your voice is analog data. Okay? Any noise that generated by the nature. Okay? Non-computers, they are all in analog form. That's why we call those data analog data. And digital data is actually the original state of data that is generated by your computer system. So anything coming out from your computer system, they are all in digital data. And then the format is 1 and 0. And analog is coming in different waveform. And analog signal versus digital signal. So what's the difference? Analog signal is just like the electrical signal that we are having. Right? And then the digital signal is actually what we call the baseband signal. That is actually the intermediate signal that we already incorporate. We already incorporate analog data into the digital data into the analog signal. Then it will actually produces a digital signal. So it's still carrying the data of digital, but the fundamental transport itself is actually still analog. And of course, when we talk about analog signal, we will have a lot of different types of signal. When you look at the word signal here, usually they refer to analog signals. And the analog signal usually having a characteristic of sine wave. They got frequency, they got period, they got phase, and they got wavelength. So these are the four characteristics of a sine wave, which is usually representing an analog signal. And for digital transmission, we will have baseband versus broadband, and then we will look at different transmission impairment as well, which is the problem of transmission, such as attenuation, distortion, and noise. So what is attenuation? So attenuation is basically your signal getting weaker and weaker. And then distortion is actually external, signal disturbance caused by external source of signal. You have external source of signal come close to each other, so they will actually having distortion. They will cause distortion to each other. And then noise. Noise is what? Noise can be coming from the environment. Noise is some unwanted signal in the environment. Most of the time, it is actually in the environment. So they will also causing problem to your transmission. And later, we look at data rate limit. Okay? How much data can your transmission media deliver? It's all defined under data rate limits. And then we have two different types of calculation. One is noiseless Nyquist bit rate. The other one is the noisy Shannon capacity. Basically, from the name, noiseless is there is no inference of noise. They do not take into consideration of noise for the Nyquist bit rate. Nyquist bit rate do not take into account noise, but for the Shannon, they do take into account noise in the channel for the calculation. So there is the true thing. One is theory, the other one is more practical. Nyquist is very much define the theoretical data rate limit, but Shannon capacity basically define the more practical data rate limit for the transmission media. Then later we look at some of the performance metrics, the network performance metrics such as bandwidth, throughput, latency, and bandwidth delay product, and jitter. Let's look at analog signal. So I think this diagram will actually represent it better. So when you actually speak, when a person speak over the microphone, then this person basically generated analog signal. You can see the signal here. Okay, the signal below. So this is actually the voice signal that is being generated by this person. And then if you want to digitize the voice, you have to go through a device called ADC, analog to digital converter. And this ADC is going to convert your analog signal into digital format. So what is the digital format? Digital format is like 1 and 0. This type of format is digital format. So how does it happen? Later we will look at it. So, and then if you want to output into your speaker, so another reverse process needs to be carried out because your computer cannot store anything that is not 1 and 0. So if you want to record your own voice, let's say if you sing a song, so you want to record your own voice and you want to record into your computers as an MP3 file. So this is actually the process that is happening. So use a microphone, connect to your computer system. And then inside your computer system, there is this component called ADC. So when you actually speak over the microphone and then when you start recording, so this ADC is going to do the conversion from analog to digital for you. So a stream of 1 and 0 will be generated according to the waveform, okay, of your voice. And then this 0 and 1 can be stored inside the computer's hard disk. And all the files stored inside your computer hard disk are all in the form of 0 and 1. Okay, there's no analog signal here. In the form of 0 and 1. And then you can store them, for example, call it a song.mp3. So this is actually stored in a digital system, which is a computer system. Then later, when you want to play back your recording over a speaker, speaker is actually an analog device. Speaker like this is actually an analog device. So you need to regenerate the analog signal again, so that this analog signal can be sent to an analog device to reproduce your song. That's why they have to go through a digital to analog conversion, so that you see the analog signal is being regenerated. But one thing that you can see from comparing this one, the original analog signal, and the system generated analog signal here. So if you compare these two, So what is the difference? You see, one is jagged a bit, one is quite smooth. You see the blue color one is actually quite smooth. That's the original form. And then the one that is in red color is actually jagged, not smooth. Okay, so those type of signal are already being generated. Why they are not smooth? It is because of during the conversion process, during the ADC conversion process, there are some loss of information. That's why the graph, the signal waveform is not smooth. And so that is the reason. That's why if you want to preserve the highest quality of your song or of your voice, then analog recording is still the best. You will be able to capture the entire spectrum. But digital encoding is good, provided they have enough sampling rate. That's why they actually higher resolution. This means if the resolution is high enough, then you will be able to capture close enough. Okay, the red color waveform here will be close enough as compared to the blue one, original waveform. So if they are close enough, then you, as a human, then you might not be able to detect the differences, because your ear is always have limitation, isn't it? So you cannot detect the difference. So it is okay to have some data loss in this conversion process, right? So this is actually how analog data are being converted to digital data. So you have to go through a device called ADC, stand for analog to digital converter or conversion, or you want to do the reverse, DAC, digital to analog conversion. Right? So about the data, okay, when you actually do analog to digital conversion, this is exactly what happened. Your analog signal is always very smooth, okay, very smooth here. And this part is very smooth. But the moment when you go into the digital part, they are not so smooth, because they actually take at this particular point. Okay, at this point, okay, all the point that I'm marking, you see, they only take value at those particular point only. So because of that, some of the information has been omitted. For example, between 63 to 78, so there is actually, these 2 points are actually separated quite a distance here. So there is a difference. That's why there is a missing of information. But roughly, after you do the conversion to digital, you will still be able to see the trend, to see the shape of your analog signal. It's just that they are not smooth. They are not smooth. But as long as, then how to make it smooth? To make it smooth, the distance of this one. See the distance here, this one, and this one. Okay, this distance here will have to be made as small as possible. This one, the one that you see on the screen, they are actually quite big, still quite big. But if you can make it even smaller, then you will have higher resolution. So when you have higher resolution, then more data from the analog can be kept. Because of that, then you will have much clearer, much more close to original source type of digital data being generated. Right? So this is actually the conversion. So always remember, when you convert from analog to digital data, there is actually some losses happen. Okay, some of the analog data will be lost during the conversion process. So that is actually common. As long as they do not lose too much until you start to hear, the quality was so bad, then that means your sampling rate is too low. Okay? But if your sampling rate is sufficiently high, for example, your MP3, usually you at least minimum go for, most of the people using 128 bits, but some people using 256, if they want to have higher resolution, so they increase the number of bits. Okay? Some people using 320 bits, for the digital encoding. This means the file size is going to be bigger. Of course, when you have increased the number of bit rate, you basically increase the resolution of your sampling. And that's why you can capture more data. That's why they are clearer. Okay, as simple as that. That's why next time when you actually choose your MP3 recording and encoding, then you know what are those bits means. Higher bits means they can actually represent more data. So more data will be preserved during the conversion process. Right, so these are the exercise. So you look at comparison of the data signal here. The analog signal is actually something look like a sine wave, but for digital data, it's either 1, 0, okay, 1, 1, then you might have 0, 0, 0, and then you have 1 again. Okay? So this is how digital signal and analog signals is different. So digital signal is also using electrical signal, but that signal has already got the characteristic of data, of digital data representation, 1 and 0. It's already being represented in digital signal. All right, periodic and non-periodic signal. I think most of the signal, if they do not carry any data, they are periodic signal. Right. Let's look at this one. Okay, they do not carry any data. They are beautiful periodic signal. This means they repeat their cycle. Okay? One cycle is from here until here. Okay? This is one cycle. Okay? The one cycle here is actually similar from this one to another one. So this cycle from here to here is actually the same. Okay? So because of that, that's why this is what we call the periodic signal. And then this signal look perfect, original. But when you put data onto and encode data onto the analog signal, for example, you put data, then it is going to change into non-periodic signal. Because the data that you loaded into the signal to be carried by the signal is going to alter the amplitude of the signal. That's why some are actually higher, this one lower, this one higher, this one lower a bit, this one very low, and then this is actually getting high, and then this one higher again. So you can see that, this has become a non-periodic signal. Usually non-periodic signal are actually periodic signal that carry data. When you carry data, so your periodic signal will become a non-periodic signal because of the integration of data into the signal. So this is actually the difference. So the signal look much more ugly after it carry the data. It is not smooth as a fixed number or cycle. And of course, some of this calculation that you need to really aware what is the period. So you look at this equation here, okay, frequency and period equation. Frequency is equal to 1 over period. So you can calculate frequency is measured in hertz. Okay. So high frequency, you can see the pattern of the high frequency. One cycle is like this. This is one cycle. Okay. This is actually the period from here to here. And then the low frequency one, you can see the cycle from here until here. So it's actually so long. When you have a longer period of time, okay, when the period is actually increases from 1 to 2, then your frequency will actually drop from 1 Hertz to 0.5 Hertz. So this is actually the difference. High frequency and low frequency. High frequency tends to have more bandwidth. So that is very common. And of course, frequency can also be related to the wavelength. So relationship of frequency to wavelength is actually same. 1 over wavelength is actually the frequency. So what is a wavelength? Wavelength is the length of a wavelength. The higher the frequency, the wavelength is actually shorter. This is high frequency. You can see from this diagram here. This one is a high frequency. That's why the wavelength is always shorter, short wavelength. So this is actually the lower frequency. So your wavelength is going to be shorter. Low frequency, your wavelength is going to be longer. Longer when you have low frequency. Longer, I would say. So phase is actually when you have two signals, they will actually change in the phase here. This is actually the phase difference for the signal. So after your signal being transmitted over a certain distance or certain transmitter, so your signal is going to run away a bit. So these are all physics. So because we are dealing with the transmission media, we are dealing with electricity. So since we are using electromagnetic signal to carry our data, so we need to understand the idea of electromagnetic signal, which is a sine wave. So you can do the exercise, but always remember these two equations here: frequency equal to 1 over period, and then period is equal to 1 over frequency. So as frequency increases, then your period is going to getting smaller period. As your smaller, as your and then vice versa. So you have periods and frequency. So they're all one high, the other one will be low. So this is exactly the same thing what we're talking about. So you'll be able to see what is the period, which is labeled as T. The period is actually one complete cycle of the sine wave signal. And of course, some of these unit that is being used, then you have to be aware. So normally when we start with second, this is 1 second, and then we'll start with millisecond, 10 power of minus 3, and then we talk about microsecond, 1 power of minus 6, and then we talk about nanosecond, 1 power of minus 9. And then of course there's a picosecond coming into the picture, 10 power of minus 12. And the equivalent frequency for 1 second is actually 1 hertz. Then you will see kilohertz, megahertz, gigahertz, and terahertz. So those are the different frequency associated with the different periods. So I'll leave the exercise to you for you to have all this your own exercise. So this is actually phase different. A signal will actually run out of phase because of the delay in the transmission. You're sure is going to experience this delay. There's no nothing which is actually 100% perfect. For example, this one is only experience a phase change of like quarter period only. But if you look at the one below, this is actually half of the period. And propagation, all the transmission signal, when they actually transmit over a transmission medium, they will tend to have propagation delay. Propagation delay is actually the delay incurred when they actually propagate from one point to another point. You know that, this electrical signal is extremely fast. But of course, no matter how fast they are, there will still be some small amount of delay that is going to happen. And then this delay caused by the transmission is actually called the propagation time. Okay? So it's the time required for your signal to travel from point A to point B. Point A is the one sending, and point B is the one that is actually receiving. Okay? So this is actually how propagation speed is actually calculated. But again, for electrical signals, they have a speed close to the speed of light. And that is actually how fast they are. It's actually depending on what type of transmission medium they are on. If they are in the vacuum, so if they are actually transmitting in the vacuum, for example, this is a wireless transmission, electromagnetic wave. In a vacuum, then they're going to have about the same speed as light. But when they actually travel over the air or travel over the copper conductor, so the speed will be discounted, as low as 50% on it, as low as 50% to 99% of the speed of light. So this is actually a reduction in propagation speed. But it doesn't really matter because this thing, what we have is actually humans find it very difficult to detect the differences in propagation delay, except when you are using a system, and the system will be able to detect these delays. But to the user, a lot of time they won't be able to feel it unless you are transmitting huge amount of data and over a very long distance. For example, if we are using satellite, you're actually transmitting your data over satellite. You know, the satellite is actually quite far away from Earth's surface. Then because of that, long distance, then you will start to feel the propagation time. But over an ordinary cable network, normally you don't feel it too much. The differences in terms of propagation time. Right? So time domain versus frequency domain. As I mentioned, usually when you want to do frequency analysis, here's a time domain analysis. So when you see time domain, you can see time domain here is actually on the x-axis, this is time, and on the frequency domain, on the x-axis, this is actually a frequency. So these two diagrams, this time diagram, this time domain graph and the frequency domain graph, they're actually referring to the same signal. They're referring to the same signal here anyway. Most of the time, depending on what you want to see. Right? Or in the time domain signal, you see this signal never change. This signal always stay at 5 all the way. Right? So you look at time domain, it's actually pretty much not so much meaningful. That's why you would like to study the signal in frequency domain, which is just one line and showing 5 here. So you look at the frequency aspect of the signal rather than you look at the time aspect of the signal. So that is actually the difference. And how do you look at see the signal as well? If you look at this another example here. So this signal here is actually come with frequency 6 Hz. So how do you know that it is 6 Hz? Frequency 6 Hz. Because it's completed six cycle in 1 second. This is 1 cycle, 2 cycle, 3, 4, 5, and 6. So this is actually 6 cycle in 1 second. So this is 6 Hz. So this signal has got a frequency of 6 Hz. So, but if you actually flip this signal around and then to represent it in the frequency domain, what you're going to see is actually this line only. See, this particular line, which is indicating 6. Because the frequency is 6, right? See, the frequency is 6. So what you are seeing is actually this one, 6. And this is actually in the frequency domain. Right. So this is actually how people do signal analysis, both in the time and frequency domain. Sometimes it is more useful to look at the time domain type of graph, and then sometimes it is more useful to look at the frequency domain type of graph, especially when you want to do frequency analysis. Frequency analysis usually using frequency domain analysis. So you want to represent frequency is very easy. So if you actually combine another signal here, which has actually 13 Hz, so you will see another line here. So this line is actually 13 because the frequency is 13, but you can see the different frequencies sitting on the same axis, on the same axis, which is axis X. Yeah. So it's actually making frequency domain analysis very much easier by using a frequency domain type of graph. And composite signal, okay? Let's understand a little bit what is composite signal. Composite signal is very easy. When a signal carry data, then that particular signal will become a composite signal, right? So when your signal do not carry any data, then there will not become a composite signal. They will become a pure signal with a pure frequency. But composite signal means a signal that has already have different frequency incorporated together, carried together, being put together, so that they will turn into a composite signal. And then one way to actually combine signal together is actually using a technique called modulator. Okay, to modulate is to combine. If you actually can look at what I'm circling, is actually the modulation process. Is the process to combine two signals together to produce a composite signal. So always remember, composite signal consists of more than one signal that is being blended together. So that one is what we call composite signal. And again, bandwidth. What is bandwidth? bandwidth from the name itself. You can see a band, the width of the band, right? What is a band? A band is a channel. Basically, a band is a channel. So, for example, if you want to connect to some devices, so they always come with a cable. So this cable will be running at a certain frequency. So that frequency is actually what we call a channel. It's actually a frequency band. And then width, bandwidth means it's the width of the band. How large is the band itself? Just like our traffic road system, right? If you have a single lane, double lane, right? So when you have single lane, so the amount of car can go through compared to you have double lane, and then the amount of car can go through at the same time, you will start to find out that double lane is actually much more efficient because double lane has got double bandwidth of a single lane. And then because of that, if you have higher bandwidth, then most likely you're going to have a higher speed transmission. So everyone is looking at this bandwidth here to offer you more bandwidth so that you can communicate at a higher bit rate, at a higher data rate as well. So this is exactly what is being meant by bandwidth. Okay? And then different transmission media, they will actually have different bandwidth. Some of the transmission media, such as coaxial cable, as I mentioned to you earlier, coaxial cable has been obsolete. Why? Because coaxial cable can only offer bandwidth up to 10 or 16 megabit per second only. Okay? 10 or 16 megabit per second only. That's why this bandwidth is not sufficient. We want more. If you want more, you have to change the type of transmission media. You have to change it to a coupled cable instead of a coupled twisted pair cable, so that you can have greater bandwidth as compared to a straight line coaxial cable. But of course, even if the coupled cable, the twisted pair coupled cable cannot satisfy you with sufficient bandwidth, you can always go for the fiber optics. And the fiber optics has got plenty of bandwidth unexplored compared to a coupled cable. Meaning to say that, the fiber optic has got better future. It's very much like a much better candidate for future-proof implementation. Right? Coupled cable, they always still have limits. But fiber optics, you know that the frequency that used in the fiber optics is actually light. You know what is light? Light is actually coming from the sun, for example. The source of light. Using lights. You can use the LED lights, laser. Those are lights to actually carry data. So when you carry your data using lights, and the lights medium offer much larger bandwidth, that's why you will have a higher speed on a fiber optic cable. Right? So this is actually the relation. Okay. And then bandwidth can be represented by in the frequency domain. If you look at this graph here, whether you know that this is frequency domain or time domain, you look at the graph here. The graph here says frequency on the x-axis. So this is actually frequency domain analysis. So you can see all the line here is all the different signal. Okay? All the lines here are all the different signal that has been incorporated into the channel. So you can see all a wide range of frequency, a wide range of frequency that has been seen on this particular channel. Okay, I will leave all the example and solution inside the slide to you, and you will have to take some time to actually go through some of these examples, and it is definitely going to be helpful to help you to understand it further. All right, let's look at digital signal. And in terms of this, we have bit rate, we have bit length. Digital signal is a composite analog signal. So these are the few elements here we want to talk about. In a nutshell, I would say, digital signal is basically used to represent 1 and 0. But they are a signal. And remember, they are a signal. They are not just data. Your MP3 file is a data. You see, it's a digital data. And your MP3 file cannot be transferred over the transmission media just like that. You see. In order for you to transmit your MP3 file over the network, your MP3 file data, digital data, will first has to be converted into a digital signal so that it can be it can be used to represent 1 and 0. So what is 1 and what is 0? Usually when we talk about 1, it is actually a positive voltage. What is a positive voltage? Usually, for example, plus 5. Okay, positive 5 volt is actually can be regarded as a 1. And then 0 voltage, which is 0, can be regarded as this is 1. And then this one can be regarded as a 0. Okay, because there's no voltage as compared to 5 volt here. Right, so this is actually the basic introductions. So you can look at this digital signal here. Digital signal also got their own waveform, but the waveform is very much discrete as compared to an analog signal. See, this is this part here is actually a positive 5 volt, and then this part here is actually 0 volt. So whatever over here, this is actually a 1. Whatever going down here, this is actually a 0. As compared to this one. That's why you have 1, 0, 1, 1, 0, 0, 0, 1. That's why you see the square type of wave of digital signal is actually be taking this form. And these are very much the baseband signal now. You see, baseband signal of this 1 and 0 using 5 volt and 0 volt, it cannot go too far, you see. When it go too far, then this 5 volt, it will, at the end of the day, it will become, lower and lower, become maybe 4.2 volt. That's when it becomes 4.2 volt, then your signal, your signal strength is basically going to become weaker and weaker. And at one point, the destination may not be able to detect that particular signal. And then because of this problem, you cannot just sending your 1 and 0, your digital data, using a digital signal. Maybe for short distance, it is okay. Okay, within your computer system, within your CPU, okay, within your computer system itself, because the distance is so short, so you can still using this type of digital signal to actually send from one device to another device inside your own computer system. Your computer system has got many components, isn't it? Sometimes data need to be sent from one component to another component inside your computer system. Then you can use this sort of digital data of 1 and 0. But if you want to go for a longer distance, and the longer distance we are talking about here is something like, maybe, 100 meters, 80 meters, 100 meters, some of it go for like a few kilometers. And then because of that, you see, you cannot use digital signal because digital signal will be depleted very, very quickly over distance. So how do we prevent this kind of problem? To prevent this kind of problem here, we are using, a digital, a composite signal. Then we need to combine your digital signal and the analog signal together. For long distance transmission, it's always using analog signal. This analog signal can travel a very long distance. So if you want your digital signal to be able to travel a long distance as well, so you have to integrate digital signal into analog signal and to form a composite signal. And because of that, you are actually taking the advantage of other signal to help you to transport your data over to the destination. It's just like you taking a bus. Like if you ask you to walk by yourself using your walk on foot to walk from Kuala Lumpur to Johor, for example, then it's going to take a very long time for you to walk, and then most of the time you won't make it. You might not have the ability to walk this distance. So how do you accomplish? Very easy. Just get on the bus lah. When you get on the bus, you are riding on an analog signal. Just imagine the bus is the analog signal. So you get on the bus. So this bus is going to help you to transport all the way from KL to, let's say, Johor Bahru. So you have no problem. Your signal will still be safely arrived at Johor Bahru. But what you need to do is actually when you arrive at Johor Bahru, you just need to get off the bus. Okay? That's why you have to get on the bus. Then when you arrive, then you get off the bus. You get on the bus in the beginning, okay, at the source. And when you arrive at the destination, then you get off the bus. So imagine this analog signal is actually the bus, okay, for all your digital data. You cannot transmit digital data directly into analog signal. You have to go through a process to convert digital data to digital signal. Then you further integrate them, integrate the two signals together using a modulator. Then the output of the modulator will produce a signal called composite signal. And this composite signal is actually the carrier signal combined with your data, right? So I hope this is actually clear to you, that you can differentiate between digital data, digital signal, analog data, analog signal. So most of the time, carrier signal. The carrier signal that you will always hear is actually the bus. Okay, so what is a carrier signal? I want to give you a very practical example. For example, I mean, all of you are actually using Wi-Fi, isn't it? Okay, you are using Wi-Fi. I think that is the easiest for you to realize what is the difference. Your Wi-Fi is connected at 2.4 gigahertz. You all understand that, oh, I'm connecting to a 2.4 gigahertz Wi-Fi. So that 2.4 gigahertz is actually the analog carrier frequency. It's actually an analog signal, and it is actually a carrier frequency. This carrier frequency is going to carry all your data. It's like a transport, act like a bus. So your bus is running at 2.4 gigahertz. It's always running at a frequency. The analog signal is always running at a frequency. Whether they are running wireless or they are running on a cable, it's the same. It's just like they're using different frequency. I just want you to realize it is here, because most of the time people don't talk about, you don't see the frequency running on a cable. But when you connect to your Wi-Fi, then you always need to know, or you are using the 2.4 gigahertz Wi-Fi, because there is another one at 5 gigahertz, you know. So because of that, that's why you are more familiar. That's why I just want to give an example that is close enough to your daily living, so that you can understand what is a carrier signal. Analog carrier signal. For Wi-Fi is the 2.4 gigahertz, right? And then your digital data is some other digital signal that you put on this analog carrier signal. And then it is that analog carrier signal that is actually helped you to deliver your data all the way over a long distance to the destination, right? So on a cable, it's the same thing. When you connect two cables together, what is running inside there is always an analog signal inside your cable. And then this cable always running at a frequency, depending on what type of system you are running. And some of the lower performance one, they are running at maybe 100 megahertz. Some of the higher performance one, they're running at 250 megahertz, that of a frequency. Okay, of course, the higher the frequency, the more bandwidth it can offer. So how fast can you run is also very much dependent on the analog signal's bandwidth itself. Imagine that carrier frequency analog signal, and then that carrier frequency running at a higher frequency. For example, 2.4 gigahertz compared to like 250 hertz, 2.4 gigahertz compared to 250 megahertz. Of course, that 2.4 gigahertz offer more bandwidth as compared to your 250 megahertz. Right. So this is actually the differences. That's why you want to talk about bandwidth. It is actually the bandwidth of the analog signal. I know this part is going to be a little bit confusing because we are talking about the most fundamental physical layer. You know? This is all happening at the physical layer, layer one of the OSI 7 layers. Layer one, we're talking about all the physical things, something that you can actually feel. The cable you can feel. Then inside the cable you got signal, and then this signal has to be analog signal. And in order for you to send digital data over, you have to first convert your digital data into a digital signal, and then from digital signal, you board it on the analog signal, so that this analog signal can carry it for a long distance. Short distance, you can use digital signal, no problem. But for long distance, such as 10 meters, 20 meters, 100 meters, then you must use a bus, which is the analog signal. No choice. That's why this is the part that you have to differentiate. If you talk about your computer architecture, if you study your computer architecture, all the data exchange between your memory to CPU, your memory to your microprocessor, all this exchange of data all happening in the digital signal. Okay, they are all happening in digital signal. There's no analog signals involved there. But the moment when the data leaving your computer system into the network, so your digital signal has to take a bus, which is get on a carrier frequency, which is an analog signal, so that they can travel a longer distance inside the network. So I want you to be clear about the differences between these two. Okay, so don't get confused about these two. I know, sometimes it is easy for me to say, but for you to comprehend, it could be quite tough if you are not aware of the differences. How come sometimes got digital signal, sometimes got analog signal, right? So this is the part that I think a lot of you is going to get confused. And physical layer is one of the hardest layer for you to study, because they involve a lot of physics. You got to good at physics and all the stuff. I think all this frequency thingy, I think you have already studied them during your secondary school, your science subject, your physics. Some of you taking physics, then you will know that, we are actually making use of some of these signal to establish a communication network. Your telephone network is the same as well. Your telephone networks all the networks are basically run on analog signal. But whether, what are the data that you put on that analog signal is the one that is actually, you are going to do the data exchange. But the basic fundamental is that they have established a network, and all the network is actually using analog signal. Right? Then whatever data you put on top of this analog signal is going to be the data that you're going to send over. Otherwise, this signal is going to be keep sending, but the bus is empty. The bus can be empty without any problem. They just keep sending. But the other end got no data, is fine. No passenger, right? It's okay. But the moment when you put your passenger, or which is your digital data or digital signal, onto your analog signal, then they will be transported to the other end. So you can see the analog signal and the network at the physical layer is actually act like a transport system. Something like a train system. You want to imagine like a train system, a bus network system. It's all the same, right? So you just need to have that understanding. All right. So this is exactly what I want to highlight over here. Let's see if I miss anything. Okay. So this is actually, okay, I think this is the part that we missed. This is actually the part that is how do you increase, the speed. We all want to send over, right? You say that, okay, now 1 megabit is not good enough. I want 2 megabit, Now I want 10 megabit. See? So how is this increase in speed be achieved at the signal level? This is actually at the signal level. You can see these two diagrams. Diagram number 1 on top and diagram number 2 at the bottom here. You can see the difference. For one, for the same period of time, if you look at this one, this is 1 period of time. For the same period of time, you look at this one, it's only 1 bit being sent, right? Right? For the 1 period of time, and then you look at the second diagram here, for the 1 period of time, the same period of time, let's say this is actually, let's see, 0.1 second. This one has got 2 bits. This one can send 2 bits. You can see now, this one can send 2 bits. The one on top sending just 1 bit, and then this one sending 2 bits for the same period of time. So which one is faster? For the same amount of time, you send 1 bit. And for the same amount of time, you send 2 bits. Of course, the one sending 2 bits is faster, right? Because in the same amount of time, you can send 2 bits. So your performance is double, right? 1 versus 2. So the one sending 2 bits is going to have double performance compared to the one sending just 1 bit. So this is how data can be actually, data rate can be actually improved at the signal level. The period for this 1 bit here is actually this long of time. And then if you look at the one below, you just have to divide them into 2. because they are sending 2 bits here. So 1 bit here, and then another bit here, okay? So you can see the amount of time divided by these 2 bits here. So eventually you're only getting half of the time. So the time you only have is getting less. So this is actually the consequence, the differences. So is it good or bad, for you to send, by squeezing the signal, by allocating less time for one bit, then you will get to send more, right? It's actually, from the performance wise, from the data rate wise, this is good because you can send at double speed or more. But at the signal level, this is not very good. Why? Because the amount of time, if you look at this one, the time for sending 1 bit on top here is actually this much. Look at this time here. The time is this much. And you look at the one sending 2 bits, the time is only this much. So the one below is actually more fragile, right? The one below is actually more fragile. It can actually be easily distorted by any noise in the environment. It is not as strong as compared to the one on top. The one on top, that 1 bit being sent across, they are very strong. That's why it's more reliable. Your data sent across the network is much more reliable using the one on top as compared to the one below. Although the one below can send faster, but your transmission may not be as reliable as compared to the one on top. So this is actually the thing that I would like to highlight. This is how they increase the speed. Okay. Of course, they are not limited to sending 2 bits. They can increase to 3 bits, 4 bits, 6 bits. So you are sending 6 bits for the same period of time. Then you are actually sending 6 times the bit rate. So this is actually how they increase the data rate at the signal level. But of course, come with a price. It's not to say this is a free lunch. It's no free lunch. If you try to do that, by squeezing more bits in the same period of time, then you're going to take the consequence of, your bits can be easily distorted by any noise. Your bits might be weaker, might be easily disturbed by any noise coming into the transmission channel. Okay. Right. So this bit interval, that's what I'm trying to say is actually there's the bit interval that we are referring. So the longer the bit interval, the more reliable the data transmission. So, the shorter the bit interval, of course, your data transmission will become less and less reliable. Why? Why they are become less reliable? Because, the time has been reduced and they can be easily distorted by any of the noise or distortion along the transmission line. All right, so some of these things I'll just leave it to you. Now we are done with the, composite analog signal, which is actually the analog signal that already carry digital signal. Then we call it a composite analog signal. The moment when they carry data, they will become ugly, multiple frequency. You can see that they have multiple frequency. This one as well, same thing, when they actually become composite. All right, let's look at the digital transmission here. So in digital transmission, we have 2 types of transmission. One is called the baseband transmission. Let's don't get confused with the one before. Okay, the one before is talking about analog signal as a transport signal. Fine, but what we are talking about now is actually the same thing, but it's just more detailed. So you want to transmit your digital data, and then that process is called the digital transmission, because you are transmitting your digital data. For example, you actually send over your MP3 files. You send over your MP3 file over the network. So that is actually a digital transmission. So digital transmission, we have 2 different types. One is baseband, the other one is broadband. So baseband is the one that I've been talking about. Your transmission of digital data is within a short distance. If it is within a short distance inside your computer, your CPU talk to your RAM, your memory, and then talk to your hard disk drive. So those can be baseband transmission. Okay, short distance using baseband transmission. And then if you want to send them out into the network, get out from your computers or get out from your laptop, entering the network. So the type of transmission that you should use is actually broadband transmission. So they are the difference here. Okay, so this is just like just now lah. There's the differences between digital and analog signals. But let's look at the real thing. The one involving broadband transmission is always involving a process called modulation. You still remember the modulation that we talked about in the early of our discussion just now? Before you enter the transmission media, you must get into a modulator. And then when you arrive at destination, you want to recover your digital data, they're usually going through a process called the demodulation, or demodulator, to carry out demodulation. So it's only the broadband transmission involve modulation process. But for baseband, they do not have. So what is baseband? Example of baseband is this one. Right? This signal here is actually a baseband signal. This is baseband. Okay? Do I have a better one? Let's see. All these are baseband, and I don't have an example here for broadband signal. Yes, I do have one. See, let's say, let me look for it. Yeah, this one. Okay, this signal is actually a broadband signal. Right, this is actually a broadband signal, and they look ugly lah. Usually they look ugly. So this is actually a broadband signal. So after you combine data and your transport signal together, then it will become a broadband signal. So I just hope that you won't get this confused. Just try to make you understand. And then for baseband transmission, it's very easy. You also have cable, see? Okay, you also have cable, but this cable is actually very short. Okay, very short. Maybe a few cm to less than 1 meter. Right? So you can still use the what we call the baseband transmissions. So usually it happens inside your computer system itself. Your computer has got so many components, isn't it? So all these components need to exchange data. So they're also connected by cable. So those are the cable are actually short distance. So they can use baseband transmission without any problem. Because baseband transmission is effective for short distance. Your signal will not get deteriorated very quickly over short distance. That's why you can still use digital signal, which is actually a baseband transmission. Remember, baseband, you transmit using digital signal into the channel. And it's for short distance. Always remember, for short distance. And for broadband transmission, it's actually you need to get on a bus, right? And then this get on a bus, depending on where, depending on what's the number of the bus lah. Let's put it this way lah. Bus got so many different number, so you will get on the correct number of the bus. Okay, then your data will get into this frequency. For example, this is the frequency that is being used. This is a frequency band that is used for the carrier frequency. Then your data is going to come into this particular frequency to combine them together. And then usually we call this a bandpass channel. A bandpass channel is running at a certain frequency. Then we call it bandpass. For example, your Wi-Fi, right? Your Wi-Fi is actually a bandpass channel. Why? Because your Wi-Fi running at 2.4 gigahertz. So that 2.4 gigahertz, there is actually a small range of frequency. It's not exactly 2.4, It's actually maybe 2.41 until 2.45, okay? 2.41 until 2.45. So that particular range For example, this one, let me write 2.41, let's say, until here 2.45. That's it. So that is the range. So that is actually your 2.4 gigahertz lah. So that is actually what we call a bandpass channel. And then the bandwidth is the width of this one lah. This is the bandwidth lah. Okay. How wide is the band itself from F1 to F2? Right. So this one will define the bandwidth lah. What is the width of the band itself? Of course, the larger, more bandwidth is being allocated. More bandwidth means what? Means faster data delivery. It can deliver more data in 1 second. Right? So this is broadband. Basically, you have to enter a bus. Broadband always refer to combining two frequencies, the original digital signal combined with a carrier signal to combine and then become a composite signal. And then this carrier frequency operate at a certain frequency band. So you just have to modulate them into that particular frequency. Right, so this is exactly what happened. So for example, here I mentioned here Cat3 UTP cable are actually running at 5 megahertz frequency. So the cable itself is running a certain frequency, signal with a certain frequency. And I think this diagram here explains a lot. So you have a digital signal here. And then for you to enter the channel, which is over here, first you must go through a digital to analog converter. Then to actually combine. It is actually basically combine. So you will have produce an analog signal. And then you look at this signal here, it's actually this signal here is actually not periodic. They're actually ugly. So this is actually a broadband signal. Then once this signal is produced, they actually input into the channel. They can actually travel into this transmission media. Then when they arrive at the destination, you can see that this is the same signal arrives at the destination. They have to go through the reverse process of analog to digital conversion before they can recover the original digital data at the destination. Right? So this is exactly what happened. You need to look at the process. Just imagine digital signal is just like the original data produced by the computer. Okay, represented by electrical signal. Your original data is 1 and 0. This 1 and 0 is just on and off. So it is not even the electrical signal yet. So you have to convert them into electrical signal into digital data. Look exactly just like this. And look exactly just like this signal. So this is actually a electrical signal. Then you have to modulate them. This digital to analog converter is actually a modulation process. It's actually a modulation process. Convert them, combine them into a carrier frequency. And this carrier frequency will be carried your digital signal all the way across the transmission medium and arrive at the destination. So you need to remember this process here. And then over the destination is actually the reverse process. So why do we want to make life so difficult to actually do so many conversion? It is because your digital signal can never travel such a long distance. It will die halfway. Your digital signal will die halfway after, after maybe 1 or 2 meters, your digital signal will be totally depleted. Cannot be detected anymore after 1 or 2 meters. It's only for short distance, only good for short distance. So we need a transport. We need a bus. Okay, we need a train or what, or you want to call it a bus also can, you want to call it a train also can. So you need a transport. So you get your digital signal, get on a transport, then this transport will carry it to travel a long distance. And this is our computer network, right? Our computer network make of a lot of transmission media, UTP lah, or all sort of cable coaxial lah. So you'll be carried by this modulated broadband signal to travel a long distance. Then when arrive at the destination, so they will have to perform the reverse process, right? So this is exactly what happened. So I hope my explanation will actually help you to understand this better. Right, so next one we look at this is actually the transmission impairment. Impairment means problem, right? The problem in the transmission will have attenuation, distortion, and noise. So these are the three terms that you probably have to know what are the differences. Attenuation, signal getting weaker and weaker when you travel distance. For example, if I ask you to walk for 100 kilometers, when you start walking, you are full of energy, but after you walk for 20 kilometers, you're already exhausted. When you're exhausted, you got no more energy. So this is exactly happened to the signal. And this process is called attenuation. The signal has been attenuated, getting weaker and weaker means attenuation, right? And then distortion is basically, there are some other signal nearby that can cause, signal, crossing. You imagine this is a signal crossing. And when signal crossing, you make signal confused. So this is actually a distortion, signal distortion. For example, if you actually use your Wi-Fi device next to a microwave oven, then this microwave oven also produces frequency, isn't it? So the microwave oven's frequency is going to disturb your Wi-Fi signal frequency. So you will have very bad reception. You have very bad reception. So those are actually the signal distortions. And then noise. Noise, as we all know, noise most of the time is coming from the environment. Any type of noise, you have white noise, you have frequency selective noise and all the stuff. They're all actually all sort of different type of noise produced by what? Produced by all sort of machinery, high and low frequency all combined, and this is become noise. Just like when you go to the markets, it's so noisy, right? Same thing when you want to talk to someone in the market, because there are so many people talking, so other people's talking will become a noise to you. Then you will have a lot of problems listening, because it's very difficult to listen because it's so noisy, right? So it's the same thing here, right? And distortion is what? When you want to talk to someone and other people come and talk to you again, so it's actually disturbing your transmission. All right, so these are the three different types. So I hope you are clear about the definition. And then they all measure in the power of the signal. The power. All the signal has got power. The units used to measure all the power are actually called decibel, dB. So a negative value means the signal is being attenuated, and a positive value means the signal is being amplified. Now you heard about amplifier, right? Every time when you connect to your audio system, I'm using an amplifier. You know what the amplifier means? Amplifier is something like a booster to boost your signal, to make your signal stronger. That's why it's called an amplifier. Okay, so you can actually use an amplifier. Exactly, you can use an amplifier to amplify your signal. And then the attenuate is actually to reduce the power of your signal. So you attenuate is actually to reduce your power. So when your signals experience a lot of noise, a lot of distortion, then the signal power could be attenuated. You see? And this is actually the equation that you can see from the diagram here. This is the equation that you can actually calculate the decibel on the signal loss in terms of dB by using this equation, 10 power of log 10 P or P2 over P1. So this is actually, so you just look at the example. And this diagram exactly explains what we are trying to say here. What's the function of an amplifier? Original signal, the length is quite high. If you look at this length here, the amplitude is actually quite high. After travel a long distance, so you can look at the amplitude of the signal has been shorter now. The amplitude of the signal has been shorter. So this signal has been attenuated. Then you can just feed these signals to an amplifier. This amplifier is going to boost your signal, give more power to your signal. And then once your signal is being amplified, you can start to see that, the amplitude of your signal is getting high again. So this is exactly how you can maintain the signal power of your signal or over a long distance. Right? So if you do not put the amplifier, so your signal will die off after some distance. It will become too weak for you to detect. Right? So it will be attenuated too much until it cannot be detected. That's why you need to put an amplifier in between. And what is an amplifier in a network? Okay, so what is an amplifier? Do you ever see a network amplifier? No, you don't see a physical network amplifier, but you can actually use a switch, a hub, a router. All the network equipment has got amplifier function. So the moment when they take in signal, before they send out the signal again, the signal will be amplified, right? So all the switches, hub lah, routers, all the network port has got a function of an amplifier. So as long as your signal entering the switch, then it will be amplified before the signal leave the switch again, right? So as simple as that. So you don't purposely go and buy an amplifier, but you can always buy a repeater. Here's a device called the repeaters. A repeater is basically an amplifier for a network signal and for network cabling. Okay, so I leave all the calculation to you. You look through all the example. Okay, the example are actually good. Distortion. Okay, distortion, you can see how the signal is being distorted. Initially, the signal are actually, see, if we look at this signal, original signal, this signal is actually combine these three together. These three signal combined together. Then you get this one. Get this particular composite signal. They look okay. But after, at the receiver, you look at this composite signal here, they are already not that good in shape, right? You look at the shape here, different, the shape being changed. You see, you look at the shape here. The shape actually getting more ugly. Why? Because of distortion. So distortion to the signal happen, you will actually make the signal distorted. Okay? Not perfect, distorted. So this is exactly what happened to distortion happen. What distortion do to a signal. And noise, of course, there are a lot of different noise in the environment. Noise can have induced noise, thermal noise, impulse noise, crosstalk. All those different type of noise are coming from all sort of sources. It can be from the random motion of electron, can be coming from a motor, appliances. Motor, running motor. Motor also can create a lot of noise and crosstalk. Okay, you have cable, you have wire next to each other. They can actually introduce crosstalk among wires. And then there is impulse noise as well. That's coming from the power line, lightning, and other stuff. So what happened to the noise? The noise is a signal as well. And this signal is going to be combined. Okay. So you look at your transmitted signal having a shape like this. Yeah, but when you receive it, the shape is totally different, you see. Why? Because you have to add the noise inside here. You have to add the noise. And it's become like this. So you see, the noise can at some point, the noise can kill your system. It can kill your signal as well. It can kill your signal entirely. Okay? And this is the calculation for a ratio of signal to noise ratio, SNR, and this is very important, So normally people talk about, how good is your signal? People always reference it to the noise power. This is actually the signal power reference to the noise power. How many times the signal power is stronger than the noise? If the signal power is equivalent to the noise power, then your transmission will sure fail. See? So your signal power will definitely need to be higher than the noise power in order for your transmission of data to be successful. So if your SNR is low, is very low, then most of the time your signal will be corrupted. Your signal will be corrupted by noise, and your transmission will most of the time full of errors. Okay, so these are example of high SNR and low SNR. You can see that low SNR is very easy. You see the signal here. This signal here is very low. The amplitude is actually very low. You see this amplitude here is very high. The amplitude here very high. Your noise is actually very low, you see. Your noise is very low. You see this one, this noise here is very high. So when the noise is very high and your signal is actually very low, so your noise can easily disturb your signal to fail your transmission. That's why you want to have your signal which is actually much stronger than your noise. And these are some of the calculations. And then data rate limits as well. So we will have Nyquist bit rate. As I mentioned to you earlier, Nyquist bit rate is actually the theoretical bit rate that is actually used to calculate how much data rate that you can achieve for a given bandwidth. So the equation, so this is theoretical. This one do not take into account noise. So you are using BPSK or QPSK. BPSK is the lowest lah. So you will have a lower bandwidth. So when you have QPSK, which actually increases the level of signal. Okay, just now that one, this is only 2 signal level. BPSK using 2 signal level only. What is this 2? This one is 1. This one is another one now. So you have 2 signal level only. So of course your data rate is going to be low. But if you increase the L to let's say 4 level, you compare BPSK 2 level, and you compare to QPSK. QPSK got 4 level here. 4 level. So when you have 4 level, of course you can transmit more data. And of course you have 16 level as well. You have 64 level. You look at the number of level that they have. Whereas more data can be transmitted. Very as simple as that. But of course, like when these 2 levels getting too near to each other, they can confuse also. Sometimes they're getting too near, noise come into the picture, noise is going to disturb them. So you will have errors. So chances for you to have errors in 64 level is higher than 16 level. And then chances for error to happen at 16 level is higher than the 4 level. And then the chances for 4 level to experience error is higher than the 2 level. So which one is more robust? Which one is more reliable? Of course, the 2 level BPSK. The 64 level QAM probably will give you a higher speed, a higher data rate, but they are not as reliable. It's actually a give and take, I would say. So for communication system, it's always a give and take. You want something reliable, you have to run at lower data rate. If you want something fast, then you must take you must face the consequence that your transmission might experience a lot of error in transmission. Right? So it's a give and take. Okay, so when we come to noisy channel, which is a much more practical channel, because in real life, noise cannot be avoided. You always will have noise. So Shannon capacity will actually give you a more practical capacity calculation, which take into account the signal to noise ratio. Okay, when signal to noise ratio has been taken into account, you take into account the noise component, the influence of noise into the calculation of capacity. Into the calculation of capacity. So you look at some of this example, then you will be able to calculate a much more practical capacity of your channel. Of course, this one, Shannon capacity, after calculation, they're going to offer a lower capacity as compared to Nyquist. Because Nyquist is theoretical. Theoretical means they are so perfect. That's why they will have higher capacity as compared to Shannon capacity, which is take into account noise, of course. When take into account noise, of course, your capacity is going to be reduced. But it is much more practical. So, in real life, Shannon capacity is actually a much more practical measurement of your capacity calculation. Okay, so I want you to look into some of the calculation here. So we will have Nyquist versus Nyquist versus Shannon. So what is the difference between the two? So you need to know what is the difference between the two. So one is under noiseless condition. The other one is a noisy condition. So that is the main difference. So which one is much more practical? Of course, the one with noisy condition is much more practical, because in this world, we cannot live without noise. Everywhere you go, there are noise. And of course, in terms of capacity calculation, the Nyquist one is going to have higher calculation in terms of capacity as compared to Shannon. Shannon calculation will give you a lower capacity as compared to Nyquist. Nyquist is ideal. All right, performance. Let's look at the last part on the performance. We will have a few of these parameters that is used for performance. So we'll have bandwidth. I think we have talked about bandwidth already. The higher the frequency, okay, the larger the bandwidth, the higher the bit per second. This means you will have higher bit rates. So our telephone networks cannot carry a lot of data. Is because of our telephone network is only 4 kilohertz bandwidth on it. So little. So you want to use it to carry data, it will be very slow. That's why we don't use telephone line nowadays to actually carry our digital data, because they are so slow, because they have so little bandwidth on that telephone cable. So we want to use a proper network cable, or you want to use a fiber optics that will be able to offer you higher bandwidth to give you higher data transfer rate. So throughput. So what's the difference between bandwidth and throughput? Throughput is actually what? Throughput is actually the actual data that going through the network point. Bandwidth is theoretical, saying that, okay, you should have this much. But how much useful data can actually get through? That one is actually measured by throughput. So throughput is actually measuring all the user data, your data. But actually the thing sent across the network is not just your data, there's a lot of network management data to be sent together. You still remember all the header and the trailer? When we look through the OSI 7 layer, they do have, every different layer, they add different header, right? So the header are actually quite long. So all this header also needs to be transmit over a network. But all those header are not being calculated for throughput. Throughput only calculate the data that go through on it. The header and the trailer that go through the network will not be calculated. They will be ignored. That's why throughput is actually measuring the user data without taking into account the header and the trailer. Okay, so now you get you know the difference. So the bandwidth bitrate, they talk about everything. They take into account all the header all the trailer. They are all combined. They don't care. They combine together. Send how many are useful, they don't care. But throughput, they do care. What are the useful data that is being sent across the network? So throughput is much more representative. Okay. So bandwidth is a potential measurement. So throughput is the actual measurement. In short. Okay, latency. Latency is actually delay. Okay, you want to talk about is delay. So what will cause a network delay is actually propagation time. Your signal, propagate over the network transmission media, and the transmission time, queuing time, processing time. Processing delay is actually your microprocessor, delay. You want to wait for your microprocessor to actually process. Of course, there is a processing delay. So you add up all the delay together. So that is the latency of your network. So basically, when you want to travel from Kuching to Kuala Lumpur, for example, okay, so you have to depart from your house, you wait for your Grab car to come, the waiting time for Grab car is a delay. Then when you get on the Grab car take half an hour to arrive at the airport, there is a delay. And then when you arrive at the airport, you want to wait for the boarding into the plane, that waiting time is a delay. And then when you board into the aeroplane, then the aeroplane fly from Kuching to Kuala Lumpur, that flying time is actually a delay. So add up all the delay together, that is actually the latency for you to travel between from Kuching to Kuala Lumpur. So it's exactly the same thing. So they add up from different components together. You add up all the different delay or different time together. So that will be the latency of the network. As simple as that. I just give you the simple term. So I believe in my video lectures I already give you the explanation. And these bandwidth delay products, they are quite unique here. So this is only applicable to actually a very fat network, but a very long round trip delay. What is a very long round trip delay? I'll give you one example, satellite. This is usually happen on satellite. If you are using satellite as your communication channel, So you have to send your signal all the way to the satellite. And this satellite are actually very far away. If you know that satellite that we use for communication, for example, we use Miasat satellite. Malaysia has got Miasat satellite, right? And then these Miasat satellites are actually located 36,000 kilometers away from the Earth's surface. So when you need to send your signal, going through that satellite. So your signal have to travel going up to the satellite is 36,000 kilometers. Then from the satellite going down to the Earth's surface again, because you know go up and down, right? So two-way. So 36,000 kilometers times 2. So it's 72,000 kilometers that your signal need to travel. That's why this kind of communication system will have a very long delay, because your signal have to travel a very long distance. And then you will have this, this satellite communication, usually they come in huge bandwidth. Huge bandwidth, that's why we call it a fat channel. The channel is not thin, it's fat. And then the channel is fat, and at the same time, they got long delay. So for that kind of network, only, so this bandwidth delay product is very important. Okay, so through this bandwidth delay product, we will be able to calculate, okay, how much we can send continuously so that we can achieve, the maximum performance over the link, so that we are not wasting the bandwidth that actually caused by the delay and all the stuff, right? So this is actually a very unique case. I just telling you in high order, in higher level, telling you that if you have that kind of a long, very long distance that of communication, then you have to really pay attention to your bandwidth product delay, which is this one. You have to do a calculation for your bandwidth product, bandwidth delay products here. You need to do a calculation so that you can continuously send to actually save your performance, right? So I think in my video lectures, I explained this one. But here, I'm just trying to tell you that the overall idea behind this. You don't want to, if I want to send, for example, I'll just give you one very simple example again. If I want to send you something and then this thing is going to take 3 days to arrive, then for me to wait for your response, the minimum day that I have to wait is actually 3 days. When I send the item, I need to wait for 3 days. Then only you will receive it. Then only after you receive it, then you are going to give me a response that, hey, I have received it, So for that 3 days of waiting, I'm doing nothing, right? I'm doing nothing by just waiting for your response. So I'm wasting the bandwidth, I'm wasting the resources. I'm wasting the network resources. And because of that, so what am I going to do now is, I know the delay is 3 days. So I'm going to send, first day, I'm going to send you something. Second day, I'm also going to send you something. The third day, I'm also going to send you something. Then I know I can send you three items. Each day only can send one item. Let's say I can send you 3 items continuously for 3 days. Then after that, I will start to wait for your reply. Then when you receive the first item, then I will get it, in day number 4. Then day number 5, I will receive the acknowledgement for item number 2. And then on day number 6, I will receive acknowledgement for item number 3. So by doing that, by continuously sending, I don't wait for you. So then I can actually send more things to you in a shorter period of time. So this is exactly what happened, right? So you have to imagine this way. And this calculation is only good when you have a high delay fat network. If the network is not fat, then it's not so much of the point. So it has to be fat. I mean, you can send a lot of data one time. Then this will be useful. And it's only applicable to network with very long delay and high bandwidth. For example, satellite network. Okay? And jitter is actually, sometimes if you order things online, it's actually the variation of time, is variation of delay. Sometimes it is faster, sometimes delay is shorter, sometimes delay is longer. It's not consistent. For example, I just give one simple example. Post Laju, right? Post Laju always promise next day delivery. Okay, Post Laju promise next day delivery when you send using Post Laju courier. But sometimes Post Laju take, okay, next day deliver. Sometimes they take 3 days. Sometimes they take 1 week. Then sometimes they take 1 day again. Sometimes they take 2 days. Sometimes they 1 week again. You know, this inconsistency in delay is what we call jitter. And this is very bad. You know. A network with high jitter is not good for time-sensitive applications such as audio and video. If you do audio streaming, video streaming, now we are doing audio and video streaming now using WebEx. WebEx is an audio and video streaming. So if our network has got very high jitter, so sometimes my voice is smooth, sometimes my voice is not smooth. So that is very bad for the network performance for our applications such as video conferencing. So it's going to be very bad. You see. That's why jitter is another parameter for us to measure in terms of the network performance. So high jitter is bad. Right? Okay. I think that's all for this learning unit. Is there any questions? Anyone? Anything? Are you still with me?
I think I have no questions, sir.
Excuse me, sir.
Yeah.
I have a question about the assignments.
Okay.
The assignment section D is the question is explain the issue performance of the technology, such as the bandwidth, latency, and jitter, those things. But we cannot find any information in the IEE. We found that the articles is more deeper. I mean, all the data algorithm, those we cannot understand it.
Okay. I think, put it this way, Put it this
Okay.
way. So when you actually, let's say you have been assigned a topic, okay? You've been assigned a topic. So let's say you've been assigned a topic on 5G, okay? For example, 5G. So you want to look at this network performance issue. So when you search for the paper, you just have to combine. You have to combine 5G and some of these performance metrics, such as bandwidth and all those things. So you have to combine together. So some of the paper they talk about it, so you can use that paper. So it's not any paper, but it's paper that is related. Okay, the paper that is related, then you can actually use it. So when you do the search, you have to combine. You have to combine, the technology that you have been assigned to, and plus the keyword that is relevant. So when you actually search for the paper, you have to combine, like let's say 5G bandwidth. For example, you just search just like that. So they will actually show you some of the relevant paper that has talked about 5G and its bandwidth and other stuff. Okay, so this is actually about searching for a suitable paper, okay, from the journal itself. And of course, you don't go too deep. Sometimes, for your case here, you just need to, you don't look at the algorithm, because I don't expect you to be able to, understand the algorithm that they talk, which is actually at the second half of the paper. Most of the time, you just look at the first half of the paper to look at, some of the conclusions that they are doing, some of the technique, introductions, background, and all those things. So those things shall be sufficient for you to actually, do your assignment already. Okay? Does that answer your question?
The introduction only suggests, it only explain the SO algorithms. We just put SO algorithm only.
Yeah, just
Don't
put
need explain.
just put the general description of the algorithm. You don't have to write down all the equation and all the stuff. It's just a general description of what is this algorithm doing.
Okay.
Usually they will talk about, the advantages of the algorithm, what this algorithm is doing and all the stuff, right? So those are the explanation which is sufficient. You don't have to go until you have to put in the equation and all the stuff, that is actually over too much already. That is too much. Yeah.
can we combine our knowledge from the Google,
Can, you can.
but the article doesn't explain anything? I mean, such as the SSL termination, those things, but the articles cannot.
Yeah. Sometimes the article are too technical. They assume the user have sufficient knowledge. So if you encounter certain keyword that you do not understand, you can always use Google to help you to actually, you can search in the Google, and then you can use those explanation that you search from the Google to actually use it as an explanation for your assignment.
Okay, thank you, sir.
Okay. Yeah, thanks for asking all those questions because at least you are clearer about what you are doing. Okay. Okay. So any more? No more. Okay. And some of you who has got not scanned your attendance, you can scan it now, just in case. If you haven't scanned your attendance, you can scan your attendance. If you have done with your attendance, then I will see you again. But make sure all of you actually sit for your quiz on the 14th of April. The quiz is in Ellipse. All right. If you have done your attendance, then I will see you again next week. Bye-bye and good luck to your quiz.
Thank you, sir.
Yep.